So I'm Cody Melton, staff at Sandia, and I've done a lot of the implementation of spin orbit in QMCPACK, so I'll be talking about both first background on how it works, both the theory and then get to a simple tutorial on a pretty simple solid state system that you can drive with Nexus. So the most important part of doing spin orbit in quantum Monte Carlo is actually using a relativistic effective core potential, a relativistic pseudopotential. So as we all know, in a normal calculation, the effective core potential removes the core electrons. And the way that it's written is a projector over spherical harmonics. So the projector is written with angular momentum indexed by L. And the way that these are actually designed is kind of demonstrated here. So what I'm showing on the right is a picture of an all electron spectrum of some atom. I think it's lead. In the first column is like the atomic energy levels of the non-relativistic Hamiltonian. So this has no spin orbit, no relativity at all. But whenever you move to something like a Dirac equation to capture relativity and actually solve for the atom, you get the normal scalar relativistic effects and the spin orbit splittings. You can see what happens to the energy levels. So you get energy shifts, kind of looking where my laser pointer is, the 1s levels shift. You can see a pretty large shift in the 6s, but also whenever you turn on relativity, you also get splitting of the p levels. So this is actually coming from the spin orbit coupling. But the way most pseudopotentials that everybody has used in quantum Monte Carlo, for example, are actually fit to a atomic spectrum that looks something like this. This is an averaged relativistic spectrum. So what they do is it captures the individual shifts of the energy levels, like the 6s shifts around, the 1s shifts a little bit, but then you average together this splitting. But you can see that like the 6p energy level is different than the non-relativistic 6p energy level. These atomic states are still represented by an angular momentum, and so you can write the projector, which removes these core electrons, as this form. But we're interested in the spin orbit term, and how do we get that in? So if you go look now at this atomic spectrum of the fully relativistic calculation, these levels are no longer represented by L quantum numbers; they're actually represented by J. So the total angular momentum L and the total spin operator are no longer good quantum numbers, so you have to move to J. So that means that if you want to include spin orbit and do it in this form where you use pseudopotentials to remove core electrons, you have to work with projectors that look slightly different. So now they have to be projectors over L and J quantum numbers. So we call these spin spherical harmonics. And this is essentially the meat of how spin orbit is actually included in QMC. We'll talk more about that later. The other thing is if you're, I said that the fully relativistic treatment does the Dirac equation. Well, the eigenstates of a Dirac equation are 4-component spinners, but do we need any of that if we're going to do this in QMC where we remove core electrons? And the answer is no, and the reason can kind of be visualized in this figure on the left. So these are the atomic states, again, of lead, and plotting out the 4-component spinners in an all-electron calculation. So you can see that there's kind of the dark solid lines, which are the atomic orbitals, and you can see that they're split into 6p1 half and 6p3 halves, or the d3 halves, d5 halves. These are the J states. But then there's these small components, which are also part of the 4-component spinner. If you look into the region of space where the orbitals would actually be participating in bonding, so kind of in this, 10 to the 0 to 10 to the 1 Bohr, the orbitals, it's completely dominated by the large component. The small components, which are these dashed lines, are completely 0. So that means that if you're going to use pseudopotentials to represent relativity, you actually don't need 4-component spinners. You can get away with 2-component spinners because the small components are effectively 0. So that's two of the things that we need. We need a relativistic pseudopotential and we need spinners. And in QMC, we'll need 2-component spinners. The other thing is now that we have spin in our Hamiltonian, we have to kind of address what happens. So if you don't have spin in your Hamiltonian, the spin operator normally commutes with the Hamiltonian, and so the total spin is conserved. And effectively what that means is whenever we write down our electrons, we can label them as up or we can label them as down. And when we are propagating that through the imaginary time evolution, an electron that is up stays up because the spin commutes with the Hamiltonian. And a spin that's down, it stays down. When we turn on spin orbit, now all of a sudden the spin doesn't commute with the Hamiltonian. And so now the spin has to be a dynamic variable that changes as you propagate the forward in imaginary time. So the spin is no longer kind of labeled as up or down. It's just a spin variable that can change throughout the calculation. So those are basically the three main things that we need. Pseudopotential that has an L dot S-like term, spin orbit. We need the two component spinners, and we need a way to sample the spin variable of an electron. So that's basically what I just said. We need to implement these in QMCPACK. So if you want to see the nitty-gritty details, we've laid this out in some papers from quite a number of years ago at this point. But I'll talk about kind of in detail how some of this works in QMCPACK first. So first is the single particle spinners. Showing at the top left. Oh no. What did I do? Okay, good. Top left is a single particle spinner. They're kind of written in this general form where we have an up component of some orbital times some spin function, where R is the spatial coordinate, S is some spin variable of the electron that will be allowed to change now because we need to sample it. And then we have a down component and a down spin chain. The standard way of thinking about spins is to think about the spin as a projection along the z-axis. So you could think about assigning a spin variable to each electron as just 1 or -1 or 0 or 1 or whatever you want to call it, just some discrete number that whenever it projects onto the spin state, it gives you a 0 or a 1. And so effectively, if you had a spin variable as +1 and it hit an up state, you could get a 1. If it hit a down state, you'd get a 0. And what that would do is you would turn on and off these up and down channels in the single particle orbital. This is kind of how the naive implementation of how you would do this. There's a problem with this, is that once you move to doing the full many-body wave function and the full sampling in QMC, you would need to sample that spin degree of freedom. And if it's discrete, if you imagine putting these spin orbitals into a determinant and then turning on and off the up and the down orbitals in the full determinant, whenever you're calculating the local energy, if you're suddenly switching out to a different orbital, you could get artificially large energy fluctuations, which could actually be inefficient for your calculation. The other option would be to actually just enumerate all the spins, all possible spin configurations for your electrons. But if you think about that, that's a 2 to the n dimensional space. So you'd have to have 2 to the n number of spin configurations every time that you would explicitly sum over in your QMC. And of course, that's exponential scaling. That is bad. So can we find a better way to represent the spinners and represent the spin variables? So the way in which we have chosen to do this in QMC is to work with a continuous representation, where now these spin functions, instead of being kind of Kronecker delta functions, now they are some complex phase, and the spin variable is now continuous. Whenever the spin hits the up state, you get this e to the is, and whenever the spin hits the down state, it gives you an e to the -is. And so your full spinner now looks like some up orbital times a phase factor plus some down orbital times another phase factor. These functional forms are chosen in a particular way such that the overlaps between the spin states give you the right kind of behavior. But it's really, really nice for sampling purposes, because if the spin is now continuous and it's just a number, it turns out you were just doing Monte Carlo sampling of an extra dimension. Instead of a 3n dimensional space, effectively it becomes a 4-dimensional space for each electron. So you have a 4n dimensional Monte Carlo sampling in real space. And that is fairly straightforward. And it kind of also gets rid of this problem with the energy fluctuations that I described, because now you're always kind of averaging between the up and the down channel in some fashion with these phase factors. So that's how we decide to represent the spinners in QMCPACK. So where do you actually get the spin orbitals to make up these spinners? Right now we support basically 3 different kind of code paths. If you're gonna do your DFT or quantum chemistry. If you're interested in doing atoms and molecules, we support the Dirac code. This is a relativistic quantum chemistry code. It has a lot of capabilities, both doing fully like normal non-relativistic DFT or quantum chemistry, but also 2-component quantum chemistry with pseudopotentials. It can do 2-component all electron, and then it can do full 4-component actual Dirac equation treatments. And it has a bunch of different Hartree-Fock and CI methods and couple cluster, et cetera. If you're interested in solid state, we support now 2 DFT codes in order to do this spin orbit calculations and get these spin components, the spin up parts of the spinner and the spin down parts of the spinner. So we support both quantum espresso and RMG. And then once we get these components, we build internal to QMCPACK, we build the spinner in this way where we kind of use the up and the down and multiply them by the phase factors. Once you have your spinner, now you have to put that into a many-body wave function. And so there's a slight change from how the many-body wave function is written in normal calculations. Normally, we have a nice, decoupling of these are my spin up electrons, these are my spin down electrons. And so the determinant can be written as this product of up and down determinants. Whenever you move to the spinners, you can't do that anymore. You actually now just have one large determinant of in electron by in electron orbitals instead of in up by in up and an in down by in down. And because of that, if you think about the normal kind of roughly cubic scaling of QMC, if you plug in for a spin unpolarized calculation where in up is in down, you can roughly see that just by moving from this into this form where you have this larger determinant gets you roughly a factor of 4 in the cost. So it is already just by moving from a spin polarized into this spinner representation, you're already buying a factor of 4 in the cost. But that's what you kind of have to do. It's just something we have to pay for. It's also important to note that the single particle spinners are inherently complex now. So as you could, kind of zoom in here, you can see the single particle spinners. We have the up orbital. These could be real or these could be complex, but because we're multiplying by this complex phase factor, the orbital is always complex. And so you can't actually run any of the QMC calculations in the real code. You have to always run in the complex code because it's always using the fixed phase approximation. I basically already said all that. Yeah, so if you are interested in doing spin orbit, you need to make sure you build the complex version of QMCPACK and always run with the QMC complex because it won't work otherwise. Okay. So I mentioned already, we have our spinners. We can build the many-body wave function out of these spinners. But now we have this continuous spin variable that we need to sample somehow. And this is talking a little bit about how the spins actually do get sampled. Feel free to stop me and ask any questions as well as I go. But the way that we do this is to, we need to come up with a way to actually sample the spin degree of freedom. So what we've done is we introduce kind of a fictitious or artificial thing we call the spin kinetic energy into the Hamiltonian. And this is chosen and written in such a way that if you can look at your normal Hamiltonian, then we also add in this sum over all the electrons and have a spin kinetic energy. It's chosen in such a way that we have this, -1/2 and some mass factor, which we call the spin mass, and that'll become important later. And then we have a normal kind of second derivative, which is, looks very similar to like a Laplacian that you would see in the kinetic energy. And then there's an offset, this +1. This +1 was chosen because whenever you actually write down this and look at the contribution to the local energy, if you sum over all these kinetic energy operators and apply that to some anti-symmetric product of orbitals, which is what a determinant is for a wave function, This is always 0. You can work it out yourself if you have our spinners that are like e to the phi times e to the is plus phi down e to the minus is. You plug that in with that +1 factor, it always cancels. So there's 0 contribution to the local energy from doing this. But choosing this form actually generates a Green's function whenever you do the importance sampling transformation. If you have worked out how to derive diffusion Monte Carlo Green's functions before. And so what that gives us is an actual Green's function for sampling the spin degree of freedom. And so now it looks like it's just another particle coordinate that gets updated as we move and do the imaginary time propagation. And so just like we have a drift and diffusion part of the Green's function to sample the spatial degrees of freedom, we now have a spin one that does the same thing. And I'll talk more about this spin mass parameter later, because this actually becomes a convergence parameter that you have to handle in the QMC. Okay, so in QMCPACK, I said we needed spinners, we needed sampling, we need the wave function. The last thing is that we need the relativistic effective core potential, the actual part of the Hamiltonian that's giving us the spin orbit interaction, the spin orbit splitting. So internal to QMCPACK, instead of working with the form that looks like this, where, as I mentioned earlier, it's written as a projector over L, J, and MJ states, we actually kind of separate out the pseudopotential into 2 different terms. One is the average relativistic, and then one is the spin orbit correction. The average relativistic looks exactly like every pseudopotential you've ever used. And so in QMCPACK, we're always using kind of the same code path for the average relativistic term. It's just a sum over angular momentums with the spherical harmonic projectors. But then whenever you kind of rewrite this in this form, you end up getting a term that looks something like this. So we have a sum, a sum over m and m prime. So we have new projectors that have 2 different m values, and then we have a matrix element that depends on the L dot S. So that's exactly where this spin orbit is. It turns out that if you're ever used to using quantum chemistry and doing relativistic calculations, they tend to write their pseudopotentials in this way, where it's the averaged plus the spin orbit correction. Whereas in the DFT world, they always write their kind of pseudopotentials in a similar fashion to this, where they're always LJ projectors. But there's a very straightforward transformation between them. The reason I mention that is that if you're interested in using any kind of either quantum chemistry pseudopotential, that if the pseudopotential library doesn't have a potential for you, and you want to do spin orbit calculations, we have to convert them either from a DFT pseudopotential or a quantum chemistry into a form that QMCPACK can read. And so you should reach out to the developers like me or Ben or somebody in order to get your pseudopotential in a form that QMCPACK can actually work with. A little bit on the implementation. It's not super important, but whenever of course, things don't look this simple in real life, so it actually looks a lot more complicated whenever you kind of write out everything. So the actual pseudopotential spin orbit pseudopotential evaluation looks something like this, but it's structured in a very similar way to how the normal non-local pseudopotential actually works. If we look here, there's a sum over quadrature points. So this is just a normal spherical kind of quadrature point that you get in normal pseudopotentials. There's a sum over angular momentum and some radial potential, which defines the spin orbit actual potential. There's a ratio of trial wave functions, that's normal. The main difference comes in that instead of you have a single sum, where you can write that as a Legendre polynomial in normal pseudopotentials, we actually have to keep a product of spherical harmonics. So there's actually a complex spherical harmonic times a conjugated one. And then you have the L dot S term. If you work out the math for our spin representation, you can figure out what these terms look like. It's not too bad. So the actual code is pretty similar to how the normal non-local pseudopotentials are actually evaluated. And then there's this pesky spin integral over here. This will be important. This is actually a really important parameter because it defines how well we actually do this spin integration. And right now what we do in QMCPACK is something very simple, I guess. is that we just break this spin integral up into a quadrature, a Simpson's rule integration. There's reasons I can get into if anybody's interested, but this actually makes the calculation a lot slower, and we have ideas about how to make this faster, but I can talk about that later if anyone is interested.
Just a quick question. Do you have a sense if there's like a factor of 2 there or a factor of 10 there? And maybe
So
in which context?
Non-spin orbit into if you run a non-collinear spin calculation in QMCPACK. So you have to have already paid for the factor of 4 roughly by moving to the larger determinant. Then it's roughly a factor of 8, because right now the default is we use 8 quadrature points in the Simpson's rule. And so you get roughly a factor of 8 from a non-collinear calculation without spin orbit to a non-collinear with. But if you're moving from like a normal calculation and directly comparing that to a fully spin orbit calculation, it's more. So it is a lot slower, but one of the tricks that you can do is actually play with that Simpson's rule integration and look at the convergence of the spin orbit Hamiltonian. I don't go into that in the tutorial, but if anyone's interested, I'd be happy to talk with them about it. And then in the future, I have some plans to actually make this go away completely by rewriting how we do this, but for now, that's how it's done. Okay. So I talked about how the pseudopotential is evaluated to actually include the spin orbit. Where do you get them? Ben's going to talk about this a little bit later, so I won't go into that too much, but basically if you go to the pseudopotential library, there's a number of files that have both the average relativistic, but then some of them also have a spin orbit pseudopotential, which has these extra terms, this spin orbit term that I'm talking about right here. And if they don't exist, reach out to one of us and we can talk about how to convert some other potentials into a form that we can use so you can actually do your calculation. It may not be a CCECP, but you know, you could do something. So that's basically the everything that you need to do a calculation in QMCPACK for spin orbit. I'm going to briefly mention some of the things that we've actually recently done in QMCPACK to enable more capabilities with the spinner and spin orbit wave functions. And one is that we actually now have orbital optimization almost ready to go. So I just wanted to highlight that. The way orbital optimization works is you apply rotation matrix to some orbital. And if you think about that orbital as a spinner, it's actually really straightforward. All you have to do is rotate amongst the individual up and the down components separately. So we've got that in the code. It's ready to go almost. There's a little bit more testing we have to do, but very soon you should be able to actually run orbital optimization, which Josh is going to explain to you how to do later. And then you could eventually just swap in a spinner wave function and do the same thing. We've also recently incorporated a number of some extra observables that talk to the spinner code. I won't go into details, or in my tutorial, I don't talk about how to use them, but nonetheless, they're there. There's a magnetization density, which could be useful to a number of people, where it actually tells you the magnetization along a given axis, both the X, Y, and the Z. You can kind of see what the form looks like, and it actually is doing our spin integration using our continuous spin. So everything is kind of formulated in that way. And then we've also incorporated a reduced density matrix, so the 1RDM in a spinner basis, if you wanted to use that. Okay, so I've talked about kind of what the theory is a little bit and some of the capabilities. So how do you actually do these calculations in QMCPACK? So I have a simple example for the solid 10. And I chose 10 because it's one of the potentials we have in the CCECP library. So one of the first things you have to do is make sure that you actually have the right potentials. So whenever you go to pseudopotential library, you should be focusing on, if they have pseudopotentials, you'll see them of this form, where there's an AREP and an SO-rep potential. The AREP is the fully averaged relativistic pseudopotential. It has no spin orbit terms. The SO-reps have the averaged plus the spin orbit. So it's the fully relativistic treatment that we need. And there's both the UPF files for the quantum espresso inputs, but then also the XML that QMCPACK talks to. And so you need to download all of those for your given problem. So in my tutorial, I put up on the GitHub, I guess I should have added a link, I forgot to, but I have a Nexus input file that's just called soc.pi in the day 2 examples to kind of walk through how to do this calculation on solid 10 with and without spin orbit. So you can see the differences between the two and what you need to do in Nexus to kind of convert your workflows from a normal calculation into the spin orbit ones. This is only an example on the solids. If you are interested in looking at the molecular systems, I have the tutorial from 2021 on how to do things going through the Dirac code and doing atoms and molecules. So if you look into that Nexus file, the first thing you always have to define is the physical system. And there's actually nothing different that you need to do in Nexus to do spin orbit for the physical system. So you define it like you normally would. There's nothing special. But then, as you know, the next step you always have to do is run your quantum espresso. But to turn on spin orbit coupling in quantum espresso, there's a few extra keywords you need. And so, as I said, in the Nexus file, I've written it in such a way that I've broken up the arguments to the code into the common arguments that every single calculation would need, and then the ones without the spin orbit coupling, and then the ones with. And at the top of the file, there's a Boolean variable that just tells you run with spin orbit or run without spin orbit. And then it will select, as you can see kind of over here, if you're running with spin orbit, it uses the common arguments and the spin orbit arguments. And if it's using the non-spin orbit, you use the common and the without spin orbit. So in quantum espresso, if you are familiar with running spin orbit in quantum espresso, you have all your normal stuff like the cutoff and your K points. You have to specify a pseudopotential, but then for the spin orbit, you also need, a spin orbit capable pseudopotential, but then also you need to turn on non-colin and L spin orb. And so those are required inputs to the quantum espresso. And so in Nexus, it's as simple as just defining your spin orbit pseudopotential and then those two flags equals true. Another important point is to actually do the wave function conversion. Most people are using PW to QMCPACK, which is the standard wave function converter. It turns out that we just haven't implemented spinners in PW to QMCPACK yet. So there is another converter that is built with QMCPACK that you can use. And it's built every time you build QMCPACK. It's called Convert PW for QMC. And it has spinner capability for quantum espresso right now. So the first thing you have to do is make sure you have compiled quantum espresso with HDF5 support. So there's a CMake flag for that. And then you just point the convert PW for QMC binary to the data file schema, which is kind of buried deep within the quantum espresso output directories. And that will generate you an HDF5 file that has the spinner information. So it's pretty simple. But it's now, if you don't want to have to deal with all that, it's also supported in Nexus. So there's a new thing. Instead of generate PW to QMC, now there's a generate convert PW for QMC. And the input looks very, very similar to how PW to QMCPACK looks. So you can almost just kind of copy the same kind of code, just switch out the name and it will work. And it will make sure all the right files are there for you. So now you have your spinner wave function, your HDF5 file that has the spinner information. So now we want to talk about how the actual QMCPACK inputs change and then how to generate that in Nexus. So there's kind of a few different spots in the XML that need to change in order to enable spinners. The main trigger is actually in the particle set. And so this is the main keyword, is that you need to set spinner equals yes. And that will tell the entire code that it's going to go everywhere in the code, go through the spin orbit path or the spinner path. And create you a spinner particle set later on, or a spin orbit SPO set later on. The other thing to note is that in your particle set, you don't have a down electron group anymore. Normally there's two electron groups. There's an up group and a down group. Now there's only one. You only need one because there's no distinction between up and down. So that's the main change, is delete your down and then put a spinner equals yes. In the actual wave function specification, a number of other things need to change. First is that you just need to point your orbitals to the convert for convert PW for QMC output, spinner HDF5 file. But then you also only have one determinant, as I said before. You don't have a product of two. You don't have an up and a down. You just have the one larger one. So in your determinant set, you need to remove the two determinants and just have one and make sure it's the appropriate size. And then there's another important point in the JASTRO. So for the two-body JASTRO, there's no longer an up-up and an up-down. There's only one. There's an up-up, or if we call it our group up, then it's an up-up. But there's also another problem, which you can read details about in our, why is it zooming? Sorry. Okay. You can read details about in our, one of our original papers is talking about the cusp conditions on the JASTRO. So the normal up-up cusp is a quarter, but for the spin orbit, it turns out you need a half. So you actually have to add this cusp explicitly into your JASTRO file in order to get it to do the right thing, because by default, it'll create a quarter. So that's a lot to keep track of. So in Nexus, all you have to do is say spinner equals yes, and it handles all that for you. It makes sure the particle set's the right type. It will go in, point it to the right file. For the spinners, it will get rid of the down determinant. It will get rid of the up-down JASTRO factor, and it will overwrite the cusp for you. So you don't have to do any of that. So tried to make this as user-friendly as possible. And then the other thing is that in a QMC calculation, you obviously need to tell it, again, point it to the spin orbit pseudopotential. So whenever you actually move into your VMC and DMC, if you remember earlier in the talk, I mentioned we added in this kind of spin kinetic energy with a spin mass that you need to somehow deal with. It doesn't contribute to the local energy, but it does impact the propagator, the Green's function. And so you can actually, you have to handle that appropriately. And it turns out that the appropriate limit is that the spin mass needs to go to infinity. So you need to, if you're doing DMC, you actually have to kind of scan that parameter and make sure it converges towards infinity, because the spin mass basically creates a spin time step. So it's basically two different time steps you have to account for. If you go back to the Green's function, you would see that relation. So how do we do this? In the QMC and DMC input, there's just a spin mass variable that you have to set. In the file, I set it up as a function. So it'll create you a whole QMC object with a given spin mass and then do a DMC time step extrapolation like you normally would see. But then you have to scan over multiple spin masses. So you have two convergence parameters that you're needing to scan. So in the example, whenever you want spin orbit, I'll set up a number of spin masses that I'm going to scan over and create the full QMC and do a time step extrapolation. And then on the next slide, I'll show you the kind of how that looks in terms of acceptance ratios and energies. But whenever you run the calculation, you'll see a normal time step extrapolation for a particular spin mass. And if you're interested, if you run QMCA, you can actually see the contribution for the spin orbit pseudopotential. It's just SOECP from the scalar.dat. Okay, so just a quick example running a small calculation. These are not fully converged. It's just kind of showing you an example. Remember that we need to look at the spin mass. So these are, each individual point here is a fully time step extrapolated calculation as a function of the spin mass. And you can see, and then on the y, at the second y-axis is the actual acceptance ratio. So the takeaway is that if you run with a too small of a spin mass, your acceptance ratio is like 40% or 80% or something. It's very, very bad, and the energies are actually higher. So this is an underconverged calculation. As I said, you have to move to this kind of spin mass going to infinity limit in order to start getting energies that agree with each other with an error bar. And so you should, as you increase the spin mass, you should see the total energy going down and eventually converge. And in this regime, the acceptance ratio is of the right order of diffusion Monte Carlo, 99% or more. So this is kind of the right regime that you need to be targeting. In this example, it was 100, but it may not be 100 in every case. So you should always check the spin mass, at least a few, to make sure that you're in the right regime and the acceptance ratios make sense. So that is all that I have. It's a fairly simple example showing you how to do a basic workflow in order to get spin orbit working. It's in the code. The example is also using the batched code, so everything is fully batched. This will not be going away whenever we move to version 4.0. Yeah, it's supported in Nexus. We have a few different observables, and we have preliminary support for OBOP, so which Josh will talk about in a little bit. So with that, any questions? Yeah.
Thank you very much, Cody. Open for questions. Fernando.
I will start with my congratulations for the nice talk and your work. I have a question. Are you using the standard accept reject algorithm?
Yes, I think so. Yes.
There's
There's nothing different in the in terms of in the diffusion Monte Carlo, like the actual advanced walkers, there's nothing really different. It's kind of blind to the fact that you're running with spin orbit or not.
I have the feeling, I actually am kind of sure you would need a drift term in the spin.
There is a drift term. There is one. Oh, I'm going the wrong way. Hold on. I'm now going the right way. So I flashed it, but I didn't actually mention it, but there is a drift term for the spins. Where's the Green's function? Here we go. So it generates, your normal Green's function. So this is like your new spin, collective spin variable over all the electrons. This is your old one. This VS is the drift. So it's a grad, it's a d by ds of the wave function over the wave. So it does have a spin drift. And so we actually, inside the trial wave functions, we actually had to add spin gradients.
Okay, great. I understood something today.
Okay. So we do have it.
Hi. I was wondering how much work is it to make estimators for this? Is it like significantly more effort to write a spin dependent estimator, or?
Not really. Ray added the magnetization density pretty quickly.
Okay.
And I've modified the 1RDM in a relatively short amount of time. So it's not too bad. All of the particle sets have access to the spins and the wave function. If you have a spinner dependent wave function, there's certain APIs that exist that are all kind of appended like with spin or something so that they tell you it has the spins included. But we can talk if you have anything that you're actually interested in using or trying to implement.
Hi, thanks for the great talk. This is really exciting. So I have a question about, I guess kind of like the workflow of, I know in Nexus, you can kind of, before with collinear calculations, you could specify like certain magnetic orientations to start with. And now that seems like it's gone, right? When we're doing calculations like this.
You can, so in quantum, like, if you started from like a quantum espresso calculation, you could specify like, I want a total magnetization of this, or, right. There's also like spin angle things.
Yeah. Getting more complicated, I guess, with
and that will all have an impact on the output spinner or wave functions that you're getting out of the quantum espresso. And then that would just be inherited by the QMCPACK. There's nothing in the QMCPACK that you would need to change. It would all come from the orbitals that you're getting out of quantum espresso.
Okay, so.
But it has, quantum espresso, the inputs can let you fiddle with those parameters. So you could drive it all in Nexus.
Does Nexus have capabilities to write scripts that have all those more complicated spin orbit coupling things in it now?
I think it has all of the input, everything that quantum espresso supports. I think it has. Yeah.
Great.
Yeah. So I think you should be able to do whatever you want.
So I'll ask a question. This is just a logistics question. You mentioned that at the minute there's a separate converter that's needed. Are there any fundamental reasons other than the availability of time that we're not using the sort of the standard route through Quantum Express or expanded a little bit?
Yeah, just haven't had time to do it. I would need to connect with EA because he's the one who wrote the PW to QMCPACK converter.
All right, anyone online? We just check there's no questions in the chat. All right, thanks, Cody, again. Thank you. Oh, one more.
So Cody, you've expressed the spin mass as a separate parameter, but I thought I remembered Lubos speaking about the possibility to kind of tie it with the time step so that as the time step gets smaller, the spin mass automatically gets larger. I would imagine that for a lot of systems, there's probably some ratio between the time step and the spin mass that would keep you in that 99+% regime. So do you think that's reasonable, or is there a reason why we shouldn't
There should
go in that
there
direction?
should be a way to do it, but you would have to investigate and test it out and figure out what that right ratio is. But I think that it could be doable and make it, make the workflow simpler so you don't have to do these 2D scans.
Okay, thanks.